let's get us started. So now that we know what viscosity is, we want to learn about viscoelasticity. This is the last example that we solved in the class together, where you have a spring and a dashpot in series. And if you remember, we looked at different possible strain versus time, and the solution was here because you have a spring which causes instantaneous deformation. Then you have time-dependent deformation because of the dashpot. When you unload, then the part which was caused by a spring elastic deformation goes back exactly this much, but the viscous deformation stays because it doesn't recover. This is a viscoelastic model because we have a viscous element and we have an elastic element together. Most materials are like that. They are neither completely elastic or viscous. And we need to learn how to describe these. And this is what we are going to start more formally, better than this today. So again, you see the reference to the textbook. So we are starting here. I just want to ask you, in particular for this part, to pay attention because the students typically find this viscoelasticity a little bit more difficult. So I know that you pay attention always, but pay extra attention here. Okay. So you have seen this before. Viscosity is like fluids. Viscoelasticity is just like the model I just showed you. When we have a part of the material behave elastic, like the spring, which is a material model, it's a material model, and a part of it behaves like a viscous fluid. And that's why it is called viscoelastic. And let's remember why we were studying this. I hope you remember that we talked about creep. And does anyone want to describe what creep is for the class? What is creep? What's the definition? How would we describe creep?
Stress stays the same, but strain grows.
Exactly. It's the increase in a strain if you maintain the stress constant. And it's a big problem, as you remember here. It's a good example, but in general, the amount of creep strain can be very, very large. So you can have this much elastic strain, but then because of creep versus time, the strain keeps increasing. First very fast, then it kind of becomes steady, and then towards the end, it can be very fast, and then the material breaks. The models that we have so far seen, none of them describes this kind of behavior. So we need to learn a little bit more. We need to have better models. It's important to know that maybe asphalt is a very easy material to see, that it is viscous, but if you increase the temperature, a lot of materials which are normally elastic, they start to show a little bit more viscous behavior. And materials like concrete and some other cementitious materials, they all show this kind of viscoelastic behavior over time. If you put a load on a concrete beam and you wait long enough, you see that the strain is increasing. So it's an important phenomenon. You have already seen it, but for example, if you have a beam, in the beginning you have, let's say, elastic deformation, you know how to calculate it, but then if you wait long enough, you are going to have increase in a strain that looks a little bit like that. It doesn't have to be in bending. even if you pull on a beam, you're going to see this kind of behavior. Concrete beams, for example, they have this kind of behavior. So it's important to remember that. Write it down for yourself, maybe that would be a good idea. Creep is increasing strain in response to constant stress. So stress here is constant. It's P over A. The elastic deformation is P over PL over EA, but then you start to have time-dependent deformation, which we call creep. Why I want to make sure that you are clear what creep is, because there is another related phenomenon which is kind of the opposite of that. So creep is stress is held constant, strain increases with time. And why is it a bad thing? It's kind of obvious, but why is it a bad thing? Can create cracking. You see like some sort of a deformed shape, and we don't like creep. There is another phenomenon very similar to creep, which is called relaxation. This is the opposite. So in this case, look here, the strain is held constant. If you keep the strain constant, it turns out that in some material, the stress starts to decrease over time, like this. This is also a manifestation of viscoelastic behavior. So it could be good sometimes. I mean, less stress could be a good thing. But there is one occasion where it is really, really bad. Can someone think about that? I don't expect it, but have you heard about pre-stressed concrete? No? So, you are juniors. So, in pre-stressed concrete, most modern concrete is pre-stressed. You have tendons, you put them in tension, and then you pour concrete over. So this is being used to put the concrete in compression, so it can tolerate more tension. Now, if the stress decreases versus time, you lose this pre-stressing stress. So the member doesn't have the properties that you think it has. I know this may not be very clear to you if you don't know really what this is about, but it could be a very bad thing in pre-stressed concrete members. I don't know if what I explained made sense to you. So you have some sort of a large bars. Imagine large steel reinforcement. You put it in tension, you pull on it, and then you pour concrete over. And then you cut the ends, so the concrete starts with being under compression. Does it make sense? And people do that because concrete is generally very weak in tension. So you put it in compression that if you apply additional tension to it, tension plus compression, it will be more towards compression, not tension. So you try to do something similar to what I told you we would do for metals to prevent fatigue cracking. It's very similar concept. Now, if your material, if your strands that you are pulling on, if they lose a stress over time, then you are in trouble. So that's one important application of this phenomenon. In any case, this is important. But it takes a long time to find out how much it will be in 50 years over the duration of the, let's say, service life of a girder. So one way to find out what's going on is to carry out experiments for 50 years, which is a little bit too long, right? And the other is to try to develop some models that can explain the behavior. And you have already seen these models. So this is just to tell you why we have to go through this phase of understanding these viscoelastic models. because we need to predict the behavior over time. One way would be to do experiments for 50 years. But 50 years, then we are already old and we don't know what's going on. The other way has been to develop these models. And we choose the second option, to develop the models. And you already have learned about models. The simple ones for linear elastic material, you have learned the model is a spring. For a fully viscous material, is a dashpot. And I kind of have already taught you also the Maxwell model, as you will see here. So we kind of want to learn about these different viscoelastic models and see which one of them is closer to the real behavior of the materials we are interested in. So let's just start with something we already know. We have a spring, you have a stress constant. This is like a creep situation, right? I hold the stress constant. I want to see what happens to a strain. Try to draw this in 30 seconds. You already know how to do this. But this time, try to also write the numbers. So how much would be the strain? When you define a model, when you have a model, you have to also have the so-called model parameters. For linear elastic material, it's very easy. It is E, for example, for the simple cases we consider. That's a material model. We need it to describe the model. Just draw the strain versus time. But also try to see how much a strain it is, not just to draw the boxcar. Try also to see how much a strain you would get. Yeah, most of you have it. Yes, I see some completely correct answer. Well, I've explained this to you a number of times before. So when we look at this, we say, okay, epsilon is sigma over E. If sigma is 0 in the beginning, when time is less than, let's say, this beginning of the loading, it is 0. And then instantaneous increase, this is linear elastic. How much? Well, stress is sigma 0, so I divide this by E, and this will be how much a strain. As long as I have the load, this strain remains sigma 0 over E, and this was in your exam. I don't know why a lot of people went down. The stress was there, so this would just go. As long as you don't unload, it doesn't go back. Why would it? Epsilon is sigma over E. As long as sigma is equal to sigma 0, then it stays like that. Right? Why would it go down? Now, in this case, it goes down. We release the load. So the moment, exactly the same moment that we release it, because this material is fully linear elastic, it has to go back to 0. Because the model says epsilon is proportional to sigma. If there is no sigma, there will be no epsilon. So here, sigma is 0. So epsilon is also 0. Here, sigma is sigma 0. Epsilon is sigma 0 over E. And here is like the other part. Sigma is 0. I know you've seen it because we are going towards more complicated models. It's very important that we understand things from the bottom up. So, I guess hopefully this is all clear for everyone. Okay. that's how it looks like. Now the dashpot. These two I've learned also. The first thing I want you to write here is the Newtonian law. What is the material model? The stress is not proportional to a strain. It's proportional to, for a Newtonian fluid, a viscous fluid, exactly. The stress is proportional to a strain rate. And the proportionality factor is lambda, the viscosity. So let's write this down. Again, this you have seen before. So, sigma, the material model, we have to put lambda here. So this would be the model parameter. Which is just a parameter which describes a Newtonian fluid. But this is called a model parameter. And sigma is equal to lambda, not epsilon, but d epsilon dt, which is a fancy way to say that how much a strain is changing with time. It's a strain rate. But we use this notation, d epsilon dt, derivative. You should be familiar with that in calculus. Now, so let's now again analyze these different parts. We have no loading, then we apply loading, we keep it constant, so it's a creep situation. I write here creep. It's like creep because I hold a stress constant and then I release it. So in the beginning, sigma is equal to 0. Then sigma is constant equal to sigma 0, and then it goes back to 0. Now, what happens to epsilon? In the beginning, sigma is equal to 0. So I write it underneath, would be nicer. So 0 is lambda d epsilon dt. So d epsilon dt is 0. And we are starting from 0. D epsilon dt equal to 0 doesn't necessarily mean epsilon is equal to 0. It means that change of epsilon with time is equal to 0. Epsilon doesn't change. If we start from 0, we stay at 0. If we start at 2, we stay at 2. If we start at 3, we stay at 3. It does not change. That's what it means. So in the beginning, since I start from 0, you kind of have to know if at the time 0 you start from 0. Now imagine we start from 0, so I stay at 0 because nothing can change. The moment I apply the stress, things change. So then sigma 0 is equal to lambda d epsilon dt. And sigma 0 is a constant. So I can say that d epsilon over dt is sigma 0 over lambda. Sigma 0 is a constant, viscosity is a constant. So that tells me that basically epsilon is sigma 0 lambda t. You just make a little integration. We start from 0, so it will be just sigma 0 over lambda times t. It's a line. And you have seen it before. So starting from the point I'm applying the load, the relationship between epsilon, y-axis, and time, x-axis is a linear relationship. It's a line. And I know that the slope is sigma 0 over lambda. So after time duration of t0, where do I get? So this is a line. I start from 0, it's the slope. To know where I get here, it would be just sigma 0 over lambda times t0. Okay? So at the end of loading, my epsilon would be sigma 0 lambda times t0. Just because this is how much I'm holding for t0, it would be sigma 0 lambda times t0. If I hold it longer, this would continue to increase linearly with time. So if I hold it for 5 seconds, it will be sigma 0 over lambda times 5. If I hold it for 10 seconds, it continues. And in the exam, for example, I never unloaded, so it had to go all the way to the end, right? Because I never put the load away. Think about the caramel. As long as you keep it in your hand, it flows. But in this case, in this problem, I'm unloading again. So we come to the kind of third regime. When again sigma is 0, I can write this equation, and the change of a strain versus time is also 0. However, I'm not starting from 0. What does it say? It says a strain doesn't change. So I got to the sigma 0 t0 over lambda, and now I know it won't change. So what happens? It just stays. I want you to make sure that you understand why, for example, here is 0, here it stays the same. E epsilon over dt equal to 0 is not equal to epsilon equal to 0. These are two different things. It's the slope is equal to 0. Okay, great. So it stays like that. It's very important that we are all comfortable with this. And now we move to more interesting models, because if you compare this to what I showed you with creep, it doesn't look like that. In other words, this is not a good material model to describe, for example, concrete creep. So we need to do something else. We need to put these building blocks together to make a little bit more complicated model. And that's what we want to do. Any questions? Everyone is very comfortable with what you see on the board here. Important. And this is how it looks like nicer. So it brings us now to the first model, which happens to be not a surprise because we saw it in that example. It is called the Maxwell model. So a Maxwell model is a spring and dashpot in series. Look what happens if you apply a load and you keep it constant. On the corner it says creep. When it says creep, it means that I'm interested in how strain is changing if I keep the stress constant. When I apply the load in the very beginning, I have elastic deformation, epsilon sub e. Then I keep the load a little bit longer. Added to that will be viscous deformation because of the dashpot, epsilon sub v. If I remove the load, what goes back is epsilon v. Now, we can write this down. So epsilon e is of course sigma over e. because of the dashpot. Epsilon V, if the sigma is constant, would be sigma 0 over lambda times T. So total strain is the elastic plus viscous for Maxwell when we have creep. So try to draw this, and this time put the amount of the strain. What is the strain? How much is it? Work with each other, talk to each other, look at the notes. This is important. How much is each point on the graph you are making? So it should look something like that, right? The beginning is 0, then you have a jump, epsilon E, which is equal to sigma 0 over E. And then this is going to go up. How much? And this is T0, right? That's the duration. So the total strain here would be basically sigma 0 over E plus sigma 0 T0 lambda. When you unload, exactly the amount of elastic strain would recover. So exactly it would be sigma 0 over E. So what you are left with would be exactly sigma 0, T0 over lambda. So make sure this is T0, because if T0 is longer, this is going to be more. So kind of a side note. Now if I change the temperature here, what will happen? The slope, what happens to viscosity with temperature? Viscosity goes down, right? I showed you graphs, I asked you about caramel. I convinced you all that when we increase the temperature, viscosity goes down. That means this slope becomes steeper. And it also makes sense because you have more deformation. It has to be. So if I would increase the temperature, the elastic deformation, E also changes a little bit, but it is compared to that, it's negligible for now, we like that. Wouldn't change much here. But then it would go much higher. But then when you when you unload, it would be again exactly be covered by epsilon E. Elastic modulus also changes with temperature, but the amount is not as much. And this is kind of the question I had asked you. A lot of people answered correctly. It was just more to think, okay, what happens when you increase the temperature? What is the effect? And you have learned that the viscosity decreases. Viscosity decreases, the slope actually increases. But even intuitively, you could think that if you increase the temperature, the material flows more. A strain will be more. Don't worry if you had issues. There were extra credit questions, and hopefully it wasn't too bad. Anyway, this was in just a side note, but the material model looks like that. Now we want to look to see what happens if the same model, so we have the exact same model, Maxwell model. In this case, we keep the deformation constant. We want to see how it behaves, how the relaxation behavior would look like. So you take the model, you bring it to a stand, and you keep it right there. And you measure how pressure will change. It turns out that the pressure actually decreases. So the stress decreases if you hold the strain constant. So here is Maxwell model. Now we are looking at relaxation behavior. Try to see if you can, I want to give you some maybe 30 seconds to think about it. Where you will start. Write down the equation for Maxwell model for strain and see what happens when strain is constant. Let's at T0. At T0, how much stress do you have? You can all calculate that. What happens? Again, the Maxwell model is series. It is a combination of a spring and a dashpot. So we start from the spring. For the spring alone, we have epsilon equal to sigma over E. Right? For the dashpot, can call it this. For the dashpot, we cannot write something for epsilon. We know that sigma is proportional to the strain rate. So if sigma is not constant, which we don't know yet, we cannot write here that this is epsilon is sigma over lambda times T. We cannot do that. Because here, pay attention, what is constant is basically epsilon E plus epsilon V. This is constant. we have these two, and we know that the summation of these, I have to write this V, is constant. So the easiest way to do that is, because I have here d epsilon v over dt, I will take derivative from both sides of that equation. So then I have derivative of, so I would take just d over dt from both sides of this equation. So then I have d over dt epsilon e. Then I have d epsilon v over dt. So I cannot write simply, I cannot sum things up very simply. Sigma is not constant. So, okay, what do? I know that epsilon, because they are in series, is the summation of both. How to get to this? I make derivatives of both sides. So this is d epsilon e dt plus d epsilon v dt. How much this will be? If something is constant, how much is its derivative? 0. So now d epsilon v over dt, very easily we know that it is sigma over lambda from this equation here. We can call this equation 1, equation 2, to make things clear. How do we take the derivative of epsilon e versus time? Nothing special, we just take the derivative. E is constant, so then we are left with d sigma over dt. You have seen this in calculus. You are just taking derivative of both sides of it. D epsilon e this is constant, comes out, this is the derivative. So now you have a simple partial, you have a simple differential equation to solve. It becomes very easy then. So then d sigma dt, which we are interested in, is, I'm just bringing e to the other side and sigma. I'll explain it one more time. So sigma would be sigma at t0 times e. This is from calculus. It has nothing to do with mechanics of materials, this part. How much is the sigma at t0? Well, in the very beginning, only the spring is engaged. So this is very simple. It's a little bit different. I don't know how much you remember from calculus, but I explain it again. So we know the relationship between strain and stress for a spring and the dashboard. Now here, the stress is not constant. What is constant is the strain. So what do? What we know for relaxation is that epsilon e plus epsilon v is constant. But I don't have anything here for epsilon e. So the way I solve this, I take derivatives from both sides. I write the derivative of the elastic and viscous strain. And then I use these two models to write these two equations. Then things become easier, because then you have a differential equation where you have only a stress and time. And this is what we were looking for. We wanted to see if we keep the strain constant, what happens? And then we have this. So It looks like that if you plot it. It starts from sigma 0, E epsilon 0. It's an exponentially decaying function. Sigma 0 E, this is what I derived for you in the previous slide. So it is exponentially decaying. There are some definitions, like the relaxation time is the time where the stress reduces to sigma 0 over E, so from sigma 0 to sigma 0 over E, this is just a definition. But the equation is just an exponentially decaying function. If you wait very, very long time, how much stress do you have? If I wait very, very, very long time, is when T becomes very, very large. How much stress do I have? 0, right? It goes towards 0. This is an exponential. This part is calculus. So if you don't remember, maybe you should look back at some of the things from before. So we start from here. At time 0, only the spring responds because it's a linear elastic material, it's instantaneous. It takes a while for the dashpot to kick in, and this is the effect. Now, what happens if I increase the temperature or decrease the temperature? So let's say if we increase the temperature, what happens? Lambda becomes if I increase temperature, what happens to viscosity, lambda? Becomes smaller. How would this curve look like then? Try to think. So this was at 50 degrees. If I increase the temperature to 90 degrees, what happens? Right. Does everyone know what I'm asking? This is for lambda. If we increase the temperature, just like in the exam, lambda becomes a smaller viscosity. I'm asking, how do you think the relaxation behavior will change? Try to draw a curve with dash lines or something like that. So this becomes a smaller. E doesn't change much. relationship between viscosity and temperature because, as you know, so now if you increase lambda, many of you gave the correct answer. So if you increase lambda, which is equal to decreasing temperature, the curves move up. What does that mean? It means that it takes longer for the stress to go towards zero at the same level of strain. That's what it means. It takes longer. Because the material is flowing less. Makes sense. And the other way around, of course, and many of you had the correct answer. If I'm increasing the temperature, the curves go inward. They are flowing faster, everything happens faster. So the stress goes back to zero faster. It makes sense, but the equations also support that. If you have here a larger number, it goes towards zero faster. It's negative. It's negative exponential. So, let's see how much time we have. We have time. So, now, to do some numerical examples for Maxwell models, let's look at this problem. The first thing I want you to do is to decide whether this is a creep or a relaxation problem. And write it down. But make sure that you understand why it is creep, because it may not be given. Especially in real life, you need to understand the difference. I didn't know it makes you so happy that I made this mistake, so it's good. It's creep. But why it is creep? Because you see there is a cylinder, given the load is constant and at the temperature. And we have the material parameters. We want to know what would be the elongation after 100 hours. And so the problem says you can approximate the behavior of the model with the Maxwell model. And it is also asking whether the elastic deformation is more than the viscous or vice versa. We are kind of out of time, but this one, I want you to work on it before coming to the class on Friday. Before, okay? So kind of to warm up